Hi everyone, my name is Ioana Delaney. Suresh and I are software engineer at IBM Spark Technology Center. This is us. We are located in San Francisco. Our main goal is to contribute to the maturity of Apache Spark. The motivation behind our work is to open up an area of query optimization techniques that rely on referential integrity constraint semantic. For that, we introduce support for informational primary key and foreign key constraints. A primary key uniquely identifies a row in a table, while a foreign key is a column or set of columns that refer to the primary key, typically in another table. These constraints will not be enforced by Spark SQL engine, rather they will be used by Catalyst to optimize the query processing. These enhancements will be targeted for applications that load and analyze data originated from a data warehouse for which the conditions for a given constraints are known to be true. Our preliminary tests show improvements of up to 8 times for some of the TPC-DS queries. Before presenting our enhancements, I would like to provide some background information about what is a data warehouse and why do data warehouses have referential integrity constraint. Typically, a data warehouse, it's a relational database that integrates data from multiple heterogeneous sources. It is designed for data modeling and analysis. The most important requirements are query performance and data simplicity. These needs are best addressed by a dimensional or star schema model. A star schema consists of a fact table referencing multiple dimension table. A fact table contains the main data or the measurements of a business, while dimension table, usually smaller table, describe the different characteristics or dimensions of a business. TPC-DS Benchmark will be used throughout our presentation. It's a proxy of a real organization data warehouse. It represents the standard benchmark for measuring the performance of decision support solutions. We will use retail product supplier as an underlying business model. And here I show part of a store sales fact table diagram from the TPC-DS benchmark. The diagram looks like a star with the fact table store sale at the center. Surrounding the fact tables are the dimension tables, which are related to the fact table by one-to-one primary key, foreign key joins. The typical constraints in the data warehouse are the unique, not null primary and foreign key. They are used for data cleanliness and query optimization. Based on their purpose, the constraints can be in one of the following states: enforced, validated, or informational. A constraint in an enforced state will ensure that all the data modifications applied to a table comply with the constraint. In a constraint in a validated state ensures that all the data that currently resides in a table comply with that constraints. An informational or statistical constraint is only used for query optimization. They work under the assumptions that the conditions for a given constraints are known to be true, and therefore the constraint does not need to be enforced or validated. How do data warehouse optimizer use referential integrity constraints? Typical data warehouse optimizer will take advantage of array constraints by implementing powerful optimization. An example will be join elimination. Here I show a simple example using a typical user scenario, queries against views. User rarely access base table directly. They use views. Views control the access to the database. This simple view lists the customer purchases in a certain year. The tables, the view joins the store, sales, fact table, and the dimension customer, item, and store. The tables are joins using a primary key, foreign key, referential integrity joins. If we only select a subselect of the columns from the view, for example, we are only interested in the items sold and not the specific store, internally the optimizer will first merge the view into the user query, and then based on the predicate primary key foreign key analysis, will prove that the join between the store and the store table is not necessary, and therefore it will remove the table store. Let's make Spark do this too. We propose to introduce some similar optimization techniques in Spark that use referential integrity semantic. Some of the optimizations presented here are star schema detection, existential subquery to inner join, group by push down through joins, and others will be referenced. Before starting presenting our enhancements, a few words about Catalyst. Catalyst is Apache's Spark optimizer. Internally, the queries are represented as three operators. So we have logical tree, physical trees. Trees are manipulated by rules. Catalyst is mainly a rule-based optimizer. Each compiler phase applies a different set of rules. For example, in the case of a logical optimization phase, which is the phase where most of our changes are, rules will rewrite logical plans into semantically equivalent one for better performance. They will apply natural, generally accepted heuristics. And another important fact that earlier rules will enable later rules. For example, by merging the query blocks, we will enable a global join reordering. Next, I will present our enhancement. I will start with star schema optimizations. Queries against our schema are expected to run fast based on the established RI relationship among the tables. In a query, star schema detection will observe the RI relationship based on the join predicate. It will find the tables connected in a star join, and then it will let the optimizer plan the star join in an optimal way. An existing JIRA 17791 implements the star schema detection based on heuristic. With RI support, we can replace the existing algorithm with a more reliable, robust one. This slide shows the transformation. A simplified TPC-DS query 25 joins table from two different schema, one corresponding to the store sales fact table, colored in blue, and one corresponding to the store returns fact table, colored in green. From the star schema diagram, we observe that the tables are connected using one-to-one RI joins. The plan on the left shows the transformation, shows the Spark execution without star schema detection. Without star schema, the optimizer will join two large fact tables early in the execution plan, and it will be forced to use a sort merge join based on the size of the inner. With star schema detection, we plan the tables connected that belong to one star schema together and into an efficient star join plan that in this case will have the store sales fact table on the driving arm and the small dimensions on the inner. This plan will result in efficient broadcast hash join over more expensive store merge join. When this query is run on a 1 terabyte TPC-DS benchmark, we observed that the execution drops from 400 seconds to 150, about 3 times improvements. Here we show our TPC-DS results with star schema detection. The results show an improvement between 2 and 8 times for this subset of queries. On the left, I reiterate some of the main benefits of the star schema detection. Again, by observing RI relationship among the tables, the optimizer can make better planning the decisions. we enable plans that not only reduce the data early in the execution plan, but also will favor broadcast hash join over more expensive sort merge join. Another transformation that uses informational constraint is existential subquery to inner joins. This transformation applies to certain types of exist and in subqueries. To understand the transformation, I show a simple example using TPC-DS schema. The query has an exist predicate, with a correlated subquery. The correlated column customer SK comes from the customer table in the outer query block. Spark will evaluate such correlated subquery using left semi-join, with the correlating condition turning into a join predicate. A left semi-join will return a row from the outer if there is at least one match with the inner. It is a general use technique to rewrite existential subqueries, but it has some limitation as it enforces a certain order of execution between the tables. In this case, the large fact table store cell in the subquery has to be on the inner of the join. A more efficient execution can be possible if we convert the subquery to a regular inner join. This will allow the optimizer to choose a better join order. Converting a subquery to an inner join is possible if the subquery returns at most one row, or by introducing a distinct on the outer rows key to remove the duplicates in the outer query after the join transformation, and thus enforcing the subquery semantic. As a key for the outer, we can use the primary key on the customer table, now available with array constraints. Another thing on the picture on the right, we observe that an inner join would also allow the tables in the subquery to be merged into the outer query block. And this in turn would allow other rules to trigger, like global join, reordering, star schema, and so on. This slide shows the transformation from subquery to an inner join for a simplified TPC-DS query 10. From the star schema diagram, we observe that the tables in the subquery and outer query block are connected using array joins. This is an indication that there is an efficient plan for their execution. The plan on the left shows the current Spark implementation. Since there is a large fact table in the subquery, the left semi-join will be implemented using a sort merge join. Instead, with inner join, the optimizer will do a global planning and choose an efficient star join with the fact table on the driving arm and a small dimension on the inner. When this query is executed, we observe a 7-time improvement. It drops, the query execution drops from 160 seconds to 20 seconds. Here we have our results for the TPC-DS 1 terabyte workload with our subquery to join transformation. This is the subset of query that have existential subqueries. We observe an average of 2 times improvement for the majority of them. And on the left, I mention again some of the benefits of subquery to join, like inner joins are more flexible and they provide better plan choices for the optimizer. The transformation avoids joins with large inner and thus favor broadcast hash joins. Also, the table in the subquery are merged into the outer query block, and this in turn it will allow other rewrites to trigger. One of them is star schema optimization. And since the transformation introduces a distinct, we observe that we will have a hash aggregate, but this result shows that Spark execute hash aggregate quite efficiently. Another transformation is group by push down through joins. This transformation will interchange the order of the group by and join operations. Pushing down a group by through join will, the benefit of pushing down a group by through join is that it will reduce the number of input rows to the join operation. On the other hand, if the join is very selective, it might make sense to execute the group by after the join. That is why this transformation is in general applied based on the cost or selectivity estimates. However, with RI join, we heuristically can push down the group by to the fact table since the number of input rows to the group by remains about the same before and after the join based on the RI condition, and the number of input rows to the join will be reduced after the transformation, and therefore it will result in an overall reduction of the execution time. Here we show our transformation using a simple query. The query computes the quantity sold, group by customer, and store. The aggregate functions are applied on the fact table column. The grouping columns is a superset of the join columns. The tables are joined using PKFK, primary key, foreign key type of predicates. In this particular case, there are no filtering predicates applied to the customer and store, and therefore, this is an indication that the number of rows after the join will not change. Based on this assumption, it is safe to push down the group by, pass the customer and store joins to the fact table. We will not push through the join with the date, since there are some filtering which will change the number of rows. This slide shows the planned transformation for our query. The numbers represent the actual cardinalities after each operator, number of rows. In this example, the group by will reduce the number of rows from 1.5 billion to 100 million, and for this simple query, we observe that the execution time drops from 70 to 30 seconds. And there are many other optimizations that can take advantage of RI constraints. RI join elimination, which I mentioned at the beginning of the presentation, eliminates dimension table if none of their columns other than PK columns are referenced in the query. Then similar, we have redundant join elimination that eliminates self-join on unique keys. Then distinct elimination if we can prove that the operation produces unique output. And with RI constraint, we can prove also that a query of subquery will produce at most one row. And next, I will let Suresh to continue with the actual implementation of RI constraints.
You see now how RI constraints help in improving the query performance. I'll quickly go over the DDL support we added to support this feature. So you can add, so we enhanced the Spark SQL DDL to allow to define primary key and foreign key constraints. You can define constraints as part of a create table. It can either be inline or out of line constraints. And if you define an inline, it will be, you don't have to specify the key columns. So here's an example for a customer table that's an inline constraint where we define the primary key. And you see out of line constraints defined for a customer demographics table. And you can also define constraints using alter table also. So you can see an example where I'm defining a foreign key constraint for a customer demographics table. This syntax is similar to what you might have observed in the traditional RDBMS systems, and this is also similar to the informational constraints DDL added in Hive 2.1. So if you notice on the alter table statement towards the end, you see two keywords, validate and rely. If you're wondering why do we need those keywords, one of the reasons why we need that validate keyword is, as Ioana mentioned before, the informational constraints, they're not enforced as part of the data ingestion. So to allow user to specify that the data actually conforms to the constraint definition, so user can specify the data is validated. So the constraints can be in two states, either it's in validate or no validate mode. And also we have an option for user to specify if the constraint should be used by the catalyst optimizer or not. So if user specifies no rely, constraints cannot be used by the catalyst. And if the state is in no validate and rely, constraint will be used only for join order optimizations, such as a start schema. But if the constraint is in the validate and rely state, constraint can be used for query rewrites, such as group by push down, join elimination, and subquery to join. So these constraints are not enforced, and they're purely for information only, and there are no backing indexes or any such things. So namespace of constraints is at the table level. So constraint definitions are stored in the table properties as key value pairs, and each constraint is stored as a JSON strings. And you can see an example of a foreign key constraints I defined on the customer table. You can see the reference table and related strings on the JSON. And the user can also find out what the constraints defined as part of the defined on the table. So we enhance the describe formatted command to include constraint information. Here is a snapshot of an example. Now that we learned how to add constraints, so we also enhanced alter table to allow to drop constraints. So here's an example for customer demographics dropping a primary key constraint, PK1. But if you notice towards the end, I have a cascade keyword. So the reason we need that keyword is by default, alter table will raise an error if there are any dependent constraints. To allow to automatically drop those constraints, user can specify the word cascade. Similarly, if you are dropping a table, and if there are dependent constraints and you want to automatically drop them, you can also specify cascade constraints. As I mentioned before, the constraints are not enforced as part of data ingestion. So we wanted to allow users to explicitly check if the constraint conforms to the data in the table or not. So we added a command for alter table, the alter table validate constraints. So what this will do is it will run Spark SQL queries internally, and if the constraint conforms to the definition, if the data in the table conforms to the constraint definition, then it will automatically change the state to validate. So if you drop a constraint or a modify constraints, the query plan can change. So if there are any cache entries that refers to an alter table, they will be automatically invalidated. So to summarize, you learned that RI constraints are a valuable addition to improve the query performance. And it's very simple to define them, and most of the traditional data warehouse systems already have defined, and if you're actually moving the data, and you can also borrow this constraint to improve the query performance. So here is a summary of the TPC-DS results that benefits from the RI constraints framework. And we observed these results on a 4-node cluster with 128 gigabit of memory. So if you would like to track the progress of this feature, you can follow the Jira Spark 19842. So we have the code under the internal reviewer, and we're hoping to put the PRs out. And if you'd like to see the demo of this feature, you can come to IBM demo booth 407. And this demo is at 4 o'clock, and we also will be around if you'd like to chat with us more about this feature. Thank you very much.
Thank you, Ioana and Suresh. We've got 5 minutes. If you have any questions, feel free. There's a mic at the end, so if you're on the left-hand side, please line up there, and I'll try to run over here on the right-hand side. Do we have any questions? 1, 2, 3. Well, thank you.